Good afternoon, everyone. I am Assistant Professor N.N. Wagule from Bhagwan Mahavidyalaya Asti, District Bidi, Maharashtra, presenting a paper on AC conductivity and drift mobility properties of substituted cobalt ferrite plus barium titanate composites. Introduction. Outline of my presentation is consist of introduction, experimental procedure, characterization of ME composite, results and discussion, and conclusion. We know that what are the composites? Composite materials consist of ferrite and ferroelectric materials. They are mixed in definite proportion and their combined property give a new property, and that is called as a magnetoelectric property. So initially, what are the ferrites? Ferrites has mixed magnetic metal oxides with iron oxide as their main component. Which these ferrite materials are very technically important magnetic properties. Ferrite possess both electrical as well as magnetic property, hence they are commercially important. On the crystallographic aspects, ferrites are classified into three major types, that is nothing but spinel, garnet and hexagonal. The structure of spinel is cubic, garnet is also cubic, and hexagonal is in hexagonal in shapes. The general formula for the spinel ferrites, garnet ferrites and hexagonal ferrites are given here. M metal ion, second divalent metal ions with Fe2O4, that is nothing have spinel ferrite, and if instead of this second valency metal ions, if I put there is a lanthanide series metal, then it is called as a garnet ferrites, and instead of that second metal twice valency metal ions, if I placed metalloids such as barium, lead like this, then it has hexagonal structures. Applications of ferrites. Ferrites plays an important role in many technical applications. There are a vast range of applications such as magnetic sensor, magnetic shielding, ferrites, electrodes and pollution control. Some of the applications of the ferrites are in satellite communication, magnetic device, electromagnetic, antenna rod and transformer, computer memory and e-spectra. What are applications of ferrite? Ferrites are applied in many fields such as magnetic sensors and magnetic shieldings, and these applications are shown pictorially here. What are the ferroelectrics? Ferroelectrics are that class of crystal which has unique polar axis, are also called as polar materials. Means in ferroelectric materials, if we applied a pressure, then they have spontaneous polarization. So the polarization can be reversed by the electric field. Means by the application of force there is electric polarization, and by the application of electric field there is a construction and relaxation in the ferroelectric materials. These ferroelectric materials have some transition temperature. Above that transition temperature, they are converted into paraelectric substances, and that is called as the Curie temperature of that ferroelectric materials. So these ferroelectric materials have polarization in the absence of electric field, and ferroelectric materials are usually non-conducting materials and may have net electrostatic polarization induced by the external electric field. And these ferroelectric materials are also extremely high dielectric constant and strong nonlinear dielectric response to the applied electric field. So what is magnetoelectric composites? The magnetoelectric composites are nothing but the ferroelectromagnetic composite material consisting of piezomagnetic and piezoelectric phases. ME effect is nothing but the induced dielectric polarization of material due to applied magnetic field on it, and this is the property in nothing but the coupling between the magnetism and piezoelectric effect. These materials have application in magnetic sensor, DC and AC magnetic fields. So for better magnetic field ME effect, magnetoelectric coefficient of ferrite and piezoelectric coefficient of ferroelectric phase must be high, and that depends on the structural properties of the ferrite as well as ferroelectric materials. When they are mixed to one another, then their product property give a new property, that is nothing but the magnetoelectric property. And AC electrical conductivity, drift mobility also an important role in this product property. So this some property is contribution of from individual component and proportional to the molar phases in these composites. So these ME composites, magnetoelectric effect is nothing but the product property, or that is the property originated from the interaction between the magnetic field and electric polarization. So how ME composite materials, magnetoelectric composite materials are prepared? Their experimental procedure is: materials are prepared by standard ceramic methods. Ferrite phases such as CO, Mn, Zn, Fe 1.604 is prepared from the cobalt oxide, manganese dioxide, Zn, zinc oxide, and ferric oxide in molar proportion as starting material, and their mixtures are sintered at elevated temperature, that is 1100 degrees Celsius for 10 hours, and then there is a formation of manganese and zinc substituted cobalt ferrites. And polycrystalline barium titanate is prepared by analytical grade barium carbonate and titanium oxide as starting material in their molar proportion, and centering temperature is 1000 degrees Celsius, and they are heated for 8 hours, and then there is a formation of barium titanate, and carbon dioxide is produced, and that carbon dioxide is evaporated into the atmosphere. Then how ME composites are prepared? So ME composites are prepared by mixing ferrite and ferroelectric phases using the formula CO Mn 0.2 Zn 0.2 Fe 1.604 plus 1 minus x BaTiO3, where x is equal to 0.00, 0.25, 0.50, 0.75 and 1.00. The mixed powders are initially pressed into die to form a pallet which has thickness about 2.5 to 3 mm and 10 mm in diameter by the hydraulic machine. Then these pallets are again sintered. The powders of these ferrite and ferroelectric phases, which are mixed in definite proportions, are used for the XRD and AC conductivity and drift mobility properties measurement. So what is this drift mobility and AC conductivity properties of these materials are measured? The theoretical background behind it is nothing but these dielectric constant of sample was calculated from the capacitance C of the pallet in farad, dielectric loss tangent tan delta, measured by the LCR meter bridge HP 4284A in the frequency range of 20 to 1 megahertz, and cross sectional area of the pallet is A, and the relation used is dielectric constant epsilon dash is equal to CD upon epsilon 0 A, where epsilon 0 is a permittivity of free space, that is nothing but 8.85 into 10 raised to minus 12 farad per meter, and AC conductivity of sample is estimated from the dielectric parameters. AC conductivity may be calculated using the relation, that is 2 phi epsilon naught epsilon dash tan delta, where tan delta is dielectric loss tangent and epsilon 0 is a permittivity of free space, omega is angular frequency, and tan delta is loss tangent. The resistivity of sample is calculated by the two-probe method using Arrhenius relation, and that Arrhenius relation is given here, that is nothing but rho is equal to, that is resistivity rho 0 exponential EP upon KT, where EP represents the activation energy, K is a Boltzmann constant, Rho is a resistivity at absolute temperature T, and rho 0 represents the resistivity at 0 degree Kelvin, and from the resistivity data, drift mobility of the substance is calculated by using the formula mu d, that is drift mobility, is equal to 1 upon ne rho, where ne is nothing but Avogadro number, rho is resistivity, and E is electronic charge. So this is the theoretical background for the calculation of AC conductivity and drift mobility of these composite materials. And when these composite materials are prepared, their structural properties also studied. The structural analysis of this ferrite ferroelectric phases, that ferrite is nothing but substituted manganese and zinc substituted cobalt ferrite and barium titanate, and their composites using the above formula are done by this XRD techniques using copper K alpha lines of which has wavelength 1.5418 angstrom. All the XRD peaks are identified and compared with the JCPDS data to confirm the phase and found have well matching. Intensity of barium titanate phases decreases with increase in percentage of barium titanate, and this indicates that there is no structural changes is observed through this composition. You can see here this XRD pattern of ferrite, ferroelectric, and their composites. These are the Miller indices such as 220, 222, 400. These are nothing but this Miller index shows that these ferrite phase is spinel in structure, while from 110, 311 and 111, these are the Miller indices of this barium titanate phase, that is which indicate that the barium titanate is also in tetragonal in shape. So this XRD pattern shows the ferrite, ferroelectric, and their composites, and from this it is also noticed that as ferrite content in the composite goes on decreasing, means ferroelectric content goes on increasing, their intensity in the XRD patterns goes on increasing, and it shows that these both phases are present in this composite separately, and they have no any structural changes observed. Then AC conductivity and drift mobility of these magnetoelectric composites are calculated and studied. The AC conductivity is studied from the frequency dependence of AC conductivity is obtained by this equation, and that equation is nothing but which is given as that equation is where that equation 2, that is epsilon dash is equal to CD upon epsilon 0. From this dielectric constant is measured, and from dielectric constant is measured, then AC conductivity is measured by omega epsilon dash epsilon 0 tan delta, where tan is dielectric loss tangent. And when this dielectric loss and dielectric loss tangents are measured from the LCR meter, then AC conductivity is measured with using above formula, and the graph is plotted between the this log of conductivity epsilon and versus log of omega square, that is nothing but square of the applied frequency and log of the conductivity. The graph is plotted between them, and this graph is shown like this, and this graph shows that as ferrite content X increases from room temperature, resistivity decreases, indicating that ferroelectric phase is most resistive, which is more important to enhance the magnetoelectric effect. And frequency dependence of AC conductivity obtained from equation and the plot clearly shows that the AC conductivity increases with increase in frequency for all frequency range. You will see here as frequency increases, AC conductivity increases. That's why it is almost a linear graph. And increase in conductivity can be attributed to the hooping mechanism in the localized sites. The conduction is due to localized electric charges carriers called as small polaron, which are responsible for good EME response. Then drift mobility. The drift mobility, the variation of drift mobility mu d with inverse of temperature for various ferrite content x is shown in figure below. This is the temperature, absolute temperature, and drift mobility mu d, and the graph is plotted, and from this it is, and the formula for the drift mobility is mu d is equal to n 1 upon ne rho, where n is the Avogadro number, E is the electron charge, and rho is the resistivity. The variation of DC resistivity and drift mobility also clear given in this table here. The variation of DC resistivity and drift mobility, and you will see there here that as DC resistivity decreases, then drift mobility also increases. The variation of DC resistivity and drift mobility of given composite is clear that the increase in drift mobility is showing the semiconducting behavior. As temperature increases, thermally activated electron increases and resistivity decreases, which results in the increase in the drift mobility. The conclusion: it is observed that better magnetoelectric effect composite should be high to get high resistivity. The AC conductivity and drift mobility, which depends on the resistivity and mole percentage of ferrite ferroelectric plays an important role in magnetoelectric effect. AC conductivity and drift mobility are investigated in the frequency range 1 kHz to 2 megahertz at 300 degree Kelvin. The AC conductivity indicates that the conduction in occurs in the ME composite due to the hooping charge carriers among the localized state. AC conductivity increases with increase in frequency. It is also confirmed that the conduction is due to small polarons. The charges which get developed in piezoelectric phase leaks through the comparatively low resistive ferrite phase. The high resistivity measurement, it is from the resistivity measurement it is clear that temperature increases, drift mobility increases, showing the semiconducting behavior, and this suggests that ferrite ferroelectric phases are present separately in composite. As temperature increases, thermally activated electron increases and resistivity decreases, and as temperature increases, the drift mobility increases, showing the semiconducting behavior. Thank you.